By charging up 2 table tennis balls covered in aluminium tape mounted on the end of polythene rods using a fun fly stick, which is a mini Van de Graaff generator, I hope to verify Coulomb's law for the force between 2 charges. To measure the force, I'm going to use the apparent change in mass on the mass balance, which I can then use to calculate the apparent increase in weight, which will tell me the size of the repulsive force between the charged table tennis balls. As expected, the size of the force decreases as I move the table tennis balls further apart, which is shown by the decrease in mass on the mass balance. The challenge is that the charge tends to discharge to the surroundings quite quickly, so I need to take the results as quickly as possible. To make it easier to take the results, I've added an enlarged view of the display of the mass balance, and I'm going to draw lines on so that we can measure the distance between the centres of the spheres. I think the table tennis balls lose quite a lot of charge very quickly at the beginning, so I'm going to leave it a moment before I start taking results. So now if I move them a little bit closer together and pause the video there, in this first position I can see that the mass is 0.22 grams and the distance between the centres of the table tennis balls is about 5.5 centimetres. If I pause the video again there, I can see that the distance is 8.5 centimetres and the mass is 0.101 grams. And pausing the video again there, I can see that the mass balance is 0.04 grams and the distance between the centres of the spheres is now 13.5 centimetres. And let's get one final reading with it the furthest distance away that we're going to do. In this position, we can see that the mass balance reading is 0.017 grams and the distance is 20.5 centimetres. Assuming that the charges remain constant, Coulomb's law says that the force should be proportional to 1 over r squared. In our case, we measured mass, which we could use to calculate the force using W equals mg, or we could say that we therefore expect our apparent change in mass to be proportional to 1 over r squared. If this is true, then we should expect m times r squared to be equal to a constant. So we can do a quick numerical test of doing m times r squared and seeing if we get constant for all our data. For this numerical test, the units don't matter as long as we keep them consistent. So let's work out mr squared for each of our data points. They're actually surprisingly consistent, which is promising in proving Coulomb's law. A possible reason that this one for the closest distance might be slightly smaller than we expect is because the charges on the spheres may move a little bit further apart because they repel each other, and so the uniform distribution can be disrupted. Another test we could do would be to plot a graph of mass against 1 over r squared and see if we get a straight line through the origin. This looks reasonably convincing as a straight line, but isn't going to go quite through the origin. I should say that 4 points is not really enough to be convincing, and maybe I should have tried to gather more, but the difficulty is the longer I take gathering the data, the more likely it is that the charge is going to discharge to the surroundings. Anyway, I hope that this might have inspired you to see if you can do an experiment to verify Coulomb's law.